Hello everyone. As you are seeing that we are looking at the quantitative aspects of queuing systems. Okay. A quantitative evaluation of such a queuing system requires mathematical characterization of the various underlying processes that drives or that constitutes that system. So, in many cases what you would notice is these 5 things that we are describing here. First, the arrival pattern of customers, right. So, if you have a system, now what is the pattern of arrivals of customers to that system? Again I recall that customer is a generic term. It could be human beings, or it could be cars, or it could be messages, it could be email, or it could be telephone calls, or anything of that sort. Then the service pattern of servers, again server is a generic one. It could mean various things depending upon the context what we mean by servers. It could mean a link, or it could mean a counter where human person is serving them, or whatever is the case, right. Then the number of servers and service channels, system capacity, queue discipline. So, you would see that in many cases like this provides an adequate description, but again this is only the very basic elements that one would look for in every system. Now, depending upon the system, there may be more than this 5 elements which you need to describe a complete system. Okay. So, out of this, the first one that we look at is the arrival pattern. Okay. When the arrivals are deterministic, which means that, for example, every 2 minutes one arrival happens, okay, then there is it's a non-random one, it's a very deterministic one, right. But generally that doesn't hold true in reality, right. So, arrivals are stochastic. So, when they are stochastic, then you need to describe them through their inter-arrival times, like the time between arrival of 2 customers, 2 consecutive customers. So, that is what we call it inter-arrival time. So, that inter-arrival time is what is required to be described in terms of its stochastic nature or random nature. For example, it could be a Poisson process, right. We will see what it is, but as of now, like currently few terms you take as it is, but we will know like in course of time what is a Poisson process. Okay. So, for example, this is one. So, where basically what we are saying is that inter-arrival times behave, or you make certain assumptions on that, and that main assumption here is that the inter-arrival times, time between 2 arrivals, 2 consecutive arrivals, is exponentially distributed. When you use that, like you will in a Poisson process, that is what happens actually. Okay. So, that is the randomness. And again, arrivals could be single arrivals or bulk or batch arrivals. Okay. So, it could mean like one by one people can come, or in case of a bus or train arriving at a station, you will see that the arrivals are happening in bulk. So, in that case you need to describe what is the bulk size. So, that is basically the size of the batch, whether it is constant one or it is random one, and if so, what is the randomness of that again. So, that is the second component that you will look at, that is this is to see whether the arrivals are bulk arrivals or single arrivals, right, bulk or batch arrivals. Okay. And again, arrival pattern over time, whether it is stationary or non-stationary. Of course, we will consider only stationary case in this course, but what do we mean by that stationary and non-stationary? It is with respect to time, whether at all times you observe the same pattern, or at different time points you observe different patterns. Meaning, for example, if you take a restaurant, right, what might happen is that morning breakfast time or during lunch time or during dinner time, the arrivals could be more in number, the pattern, and the rest of the time you will have very less number of arrivals. So, if you assume that throughout the day, right, throughout the day, it has the same pattern, meaning that any time is like any other time in some sense, then you have a stationary situation, right. So, the Poisson arrival, simple Poisson process arrival is basically we were in stationary pattern. It is basically with respect to time we are talking about, right. Non-stationary, suppose if it is not the case and it is dependent on time. So, it could mean that at various different time points, for example, of the day, you have different arrival patterns, so which is basically we describe through the rate of arrivals per unit of time, no matter whatever unit that you are taking it up, right. So, it could be non-stationary. So, in reality you would see that non-stationary is what is happening, but then again what is the exact pattern of this non-stationarity, again one has to do a lot of studies on that. But to get a first hand understanding of the system, always like one might always take the average rate to be the rate of arrivals for the whole time period duration that you are considering. So, in that case one could assume stationary, and that is how like you can assume that stationary is what the arrival pattern that you will have. Of course, in this course like we are considering only stationary arrival process, but these are the other word could be an appropriate word, could be like a time independent and time dependent one in this particular case. That's the third component in the arrival pattern that you are looking at it. Then you have the customer behavior upon arrival to the system, right. The customer could behave differently when he arrives to the system to get the service. Okay. As soon as he comes, he observes that the queue, and he sees that there is a long queue waiting, and he says, oh, this is not going to work for me, like I am going to quit right away, and then I am going to I am deciding not to enter the queue, right. So, that phenomena is what is called as balking. Balking in queuing means, or in general means, that you decide not to enter the queue. Okay. So, this is one phenomena. Okay. Now, what you do, right, you join the queue. Okay. For some reason you decided, you join the queue and you wait for some time, and after some waiting for some time you lose your patience, and then you see, okay, now I cannot wait anymore, I am going to leave the queue, I am going to exit the queue at this stage, right. So, that phenomena is what is called as reneging. Reneging means that you join the queue, and after spending some time in the queue, then you decide before you get the service. Of course, in the meantime, if you get the service, you will get your service done and you will leave. But your service it not yet started, so then you said, okay, fine, I cannot wait anymore, I may have something else to do, so you just decide to leave, that is after joining the queue. So, that phenomena is called reneging. Then there is a third phenomena, like this is called jockeying. Okay. What is that? So, suppose if you go to say in an airport or in a supermarket, there you see that you are seeing multiple queues against or in front of the multiple servers. Then you will see that, okay, you join in one queue, then you see that the other queue is moving faster, so then you just move to the other queue, right. So, after spending some time in one particular queue, it is in a multi-server scenario only this can happen. In single server, of course, there is no jockeying that can happen. So, multi-server, after spending some time in the queue, then you decide that, okay, fine, I am that particular queue is moving faster, so I am going to switch to the other queue. So, that is what is called as jockeying, that is switching between different queue. All these phenomena like are what broadly can be grouped under customer impatience, right, customer impatience. But in the first two cases he is actually abandoning, so that could also be called as queues with abandonments. The third one is he is not really abandoning the system, but he is abandoning a particular queue. Okay, so that's a little bit more finer if you want to look at it. But all three of them falls under the case of impatience. Okay. Then there could be dependency between arrival and dependency on queue length. Okay. So, there might be like between the first arrival and the second arrival, right, there may be some relationship, or between first arrival and the 10th arrival there may be some relationships. Okay. Whether these are completely independent or otherwise, one can have that kind of scenario. For example, if you take the internet traffic, it is known to be exhibiting some sort of dependency, right, and likewise in many situations you would find. But the easier thing to model is assume that independence, but if you want to incorporate the dependency, then one can do that. So, that is what dependency between arrivals. Maybe one arrival might trigger something more of the similar kind of arrivals, right. So, if you are looking for some disease being detected and then you consider that as an arrival, now like the moment you see a particular person is infected and you have found, and then you will see that in that there might be in that particular location you might find more number of such cases might be depending upon the disease, right. So, there could be dependency in simple scenario. Similarly, dependency on the queue length, right. There may be some mechanism by which the arrivals are controlled in some way, or the customer himself or the system itself operates in such a way that the queue length is also playing a role on the arrival pattern. So, these are all some simple descriptions, but there could be many more even with respect to arrival itself, in which the arrival pattern itself, in which which can describe the arrival pattern. Okay. So, one needs to completely describe what is the exact nature of arrival. So, because like any mathematical model, a queuing model also relies on certain assumptions. It is exact to the assumptions, right. So, the moment the assumptions are violated, the model is no longer valid, right. One has to completely describe what is the nature of arrivals after observing the phenomena in systems that you would see that. Okay. Now, the second component here is the service pattern. So, pretty much whatever we have seen with respect to the arrival pattern, it also holds true for service pattern, right. Again, service times, if they are deterministic, or it means it is constant, that means there is nothing much to analyze. So, things are very well predictable in some sense, right. So, the service times are in general stochastic, and again they are described through service times. So, the simplest one is assuming that to be an exponential distribution, for example. So, service time, I mean duration of the service time, right, the duration of the service that your customer is getting from the server, that duration, the time is what is service times. So, pretty much all these inter-arrival times and service times, any non-negative random variable can come in place, okay, but the simplest ones are exponential. So, they are inter-arrival times and here service times for this case, okay, right. So, they are service systems as a whole also says, I mean most of them are stochastic. So, obviously, these service times described through a stochastic random variable or stochastic phenomena. Now, again the service could be in bulk or single, right. So, bulk here would mean, for example, same example that you can pick it up, like when the train leaves or when the bus departs, or a jungle safari, like when the safari leaves. So, the customer, for example, in case of a train or jungle safari, people might come one by one singly, or maybe smaller batches as well, but on a bigger batch size, it leaves. So, which means that the service is done, for example, a ferry which is crossing the river from one side to the other, right. So, this is all you could see that the service happening in bulk. So, now again the bulk, what is the batch size, what is the group size. So, that is described through the size of the batch. Okay. So, that can happen, and also service pattern over time, whether the service again is rate of service if you look at it. So, the service could be stationary or non-stationary, that means that it could depend on time or it may be independent of time. So, we consider again in this particular case the stationary case only, right. Okay. Now, as opposed to that, there could be also dependency on the number of customers waiting for service, right. This is typically these are all called as state dependent. Okay. Again, for the arrivals and services. Okay. For both it could be state dependent, right, as we said state means the state of the process or the state of the system. So, dependency on the number of customers waiting for service. So, either it could expedite or the server may start serving at a faster rate, or it can happen in the other way around, like you could find an example. So, all these things like it is called state dependent services. Okay. So, maybe like as the experience is gained by serving few customers in the beginning, the rate of service might become more efficient. So, it becomes more number of customers can be served, or after seeing the queue you are increasing, or you get some help from someone to increase the service rate, or and so on. Like there could be many ways that you could model. Okay. So, again this is all broadly the service pattern, whatever we looked for that into this case. Again, with respect to server something might happen, of course that's are all further things, but whatever happens with respect to the service part, right. So, if you describe it completely, then only like you are described completely about the pattern of service that you have. Then the third ingredient is that number of servers. So, this could be an infinite number of servers, which is basically representing a self-service kind of systems, or there could be a finite number which could be even one server, or it could be some 10 servers or some finite number of servers. Okay. So, that is the number of servers. Okay. This is another description that you need to make. So, this is basically, as you know, like this is number of servers depends on a fundamental trade-off, which is cost to the business versus reduced delay. You have more server in place, you have less waiting time for the customer. You have less number, you will have more. Now, like what you do in such a case, like if it is a pure economical situation decision, then you can simply make trade-off. But in some cases, again you will not be able to increase the number of servers. Okay. Then one has to look at other other aspects. But if it is possible, if it is a business manager's decision to decide the number of, then one can have this trade-off between that, then one can decide the number of customers into this case. Another description with respect to this number of servers is how the waiting lines or queues are configured in the system. Okay. Say for example, in a multi-server system, whenever one more thing that we want to say before we go further is number of servers. When we always mean parallel servers in general, it goes without saying throughout, unless otherwise mentioned, that number of servers we mean always parallel servers, not sequential ones, right. So, it is always they all have equal opportunity whenever there is a customer comes, unless it is done otherwise. So, in a multi-server system, when you have all these parallel servers are there, whether they are fed by a single queue or each server is fed by its own queue or a hybrid model. So, this is how the configuration of the waiting lines or queues, which is also part of this part of description. Say for example, when it is a all servers are fed by a single queue, you can think about a saloon where you will be waiting, many people will be waiting, and then suppose there are 5 hairstylists who are there in that. So, then you can think that anyone, all of them are parallel server means you are saying that they are all in some sense homogeneous group of servers, means everyone can do all the work that is supposed to be done in that salon. So, these are all further assumption if you want to go deeper and deeper, how you are assuming. Okay. Now, if that's the part that you have here. Okay. So, then like in such case, like the common waiting line is what then you will be having. As opposed to that, suppose if it is a grocery store or something, then there might be each server is fed by its own queue. It can happen in other places as well, or a hybrid situation where, for example, if you are in an airport, like if you are going out of country, and if you are at immigration check, then you will see that there is a queue, common queue, and again you can even think in domestic level, like you could have this security check part where there is a common queue and you are being fed into another smaller queue for your checking, right. So, you could have a hybrid situation. These kind of things can happen. So, this is how like the part of this description. Okay. So, whenever we say that parallel servers are there, like we will assume in many cases that it will be fed by a single queue, or if it is otherwise, then we will state explicitly that each server is fed by its own queue, or if this is the case, then hybrid nature and so on. Okay. So, this the third component of the description of a queuing system. The fourth one is the system capacity. Whether the system capacity means like how many customers can be there in the system at any point of time. When we talk about system, as we already pointed out, it consists of the queue plus the ones who are in the service, the ones who are waiting for the service and the ones who are in the service. This is the whole system capacity. This is what we call it as the whole system, and whether there are infinite capacity for customers to wait. Again, in reality, there is nothing like an infinite capacity, but a very large one can be approximated easily by an infinite capacity, and as you will see, like the analysis also might become easier, but again it is approximation in some sense, right. So, what you are assuming that there is to be infinite capacity for customers to wait, or there is a finite capacity. Now, whenever there is a finite capacity business, right, so you have a scenario which is called blocking, so common in say computer and communication network or data networks or mobile networks and so on, because there is a capacity limit, right. So, the link between between two nodes in a network, the nodes could be anything, like it has a finite capacity, which is it has a finite bandwidth, right, through which only up to which only like things can be transmitted. So, when you try to make a call, all these lines in this route are busy, meaning that it has reached that capacity and you cannot transmit anymore, right. So, that is the finite capacity system, right. Okay. So, that is the part that you can look at basically as the system capacity, whether it is infinite or finite, though in reality things will be finite. It will be more realistic if you assume that finite and study the behavior of this one, the blockedness, because what is the probability in such situation that this phenomena, suppose what is the probability that if a customer were to arrive at a particular time, what is the probability that he would have been blocked. So, the system capacity should be such that this is bounded by some very small number. Of course, all this is what we call quality of service, right, quality of service. So, there are regulators who describe this quality of service parameters in the sense that they need to meet this requirement, right. That is what you would call a good service in some sense. So, to do that you have to arrive at that. So, in that case you have to assume that to be finite server and obtain this probability and then see whether it meets the requirement. But you would assume for analysis, simple analysis kind of thing, you can assume that to be infinite as well, right. So, these are the fourth component rather. Now, the fifth component is what we call the queue discipline. So, this describes the manner in which the customers from a queue are selected for service. So, the most common one that you would see across various applications or various systems is what you call first come first served or in short FCFS, first come first served, or first in first out, FIFO. Right. So, this is what is the most commonly that you would see, and you might feel that this is the most fair system that you might have when you have a queuing system, or when you have to queue, when you have to wait, right. But there could be different other, there could be other kind of queue discipline depending upon the application that you are trying to analyze. The other one could be, for example, the last come first served. Suppose if all it is a inventory, for example, you are making some products and then it is an inventory items. It does not matter which item that you are picking it up. So, when stocks are piled, probably the last one is what then you would pick for further processing. So, it is last come first serve. There could be random selection, right, depending upon the scenario, and there could be so, basically in the random selection it does not happen. So, if there are n customers or 10 customers are waiting, so all 10 could have equal probability of being selected. And processor sharing, which is so common in computer and communication network, right. So, it is called processor sharing, in which the server processes all jobs or all customers, or serving all customers, or processing all jobs. In computer communication or network parlor, like you would call this as jobs rather than customers. It's so common, but we will use customers rather. So, all customers or all jobs are being handled by the server simultaneously. Okay. So, this is common. Now, whenever you are working on 2 customer, or when you are working on 2 jobs, and whenever you are working on 10 jobs, obviously the rates are not going to be the same. So, the existing capacity is being distributed to 10 different customers, right. For example, if you have an the internet bandwidth, that link, that if there are only 5 customers who are accessing that, obviously you are going to get higher speed, and if there are 100 customers who are accessing the same link, then obviously the existing capacity is being distributed across these 100 people. So, obviously the rate the speed that you realize from your end is obviously slow, right. So, you have such scenario, which is what is called processor sharing phenomena or queuing discipline. Then there is this polling or round robin systems, right. So, you have systems like this, right. There is queue here, there is queue here, there is queue here, there is queue here, right. So, what happens here, like the server, he rotates between these different servers, and then he serves. It may be one customer. After serving one customer, he may move to the one customer here, and then he may move to the other customer here, then one customer here, then come back to this again. Or it could be a group of customer. That group, either by group size you could decide, or time duration you would decide, right. Say for example, if you are looking at a traffic junction, right. So, this typically is what you are seeing it here. So, this is what is a scenario which is called polling or round robin. Within that queue, of course, obviously then you will have the system again, that whether first come first served, or you stand here and someone come from behind, you just moves in front and then he gets service first. Things can happen in very complex situation if you cannot describe completely everything, right. But you need to have certain basic major features be done. So, if this is the case, this is what is called polling or round robin systems that you would have. And then you have this priority, right. So, there could be different classes of customers. Again, the service arrival pattern, we could have said that actually there could be different classes of customers who are requiring different kind of service requirement based upon that. Okay, that basically imposes in some sense the priority means. So, basically some customers may be more high in value or whatever is the reason, right. So, they do get priority. You do see, like in a hospital situation, of course, priority customers are those who need immediate care, right. So, that is the case. So, priority is prevalent, and priority customer, priority is as a discipline, also one needs to keep that in mind. Now, when this priority happens, there could be two things. One is preemptive and non-preemptive, right. The first word is preemptive and the second thing is preemptive. Means, what happens to the customer who is of lower priority and who is currently getting served. What happens to this particular customer when a higher priority customer arrives? Suppose if this particular lower priority customer service is interrupted to start the service for the higher priority customer, that is a scenario that we call preemptive. Okay. And if that does not happen, even though he is higher priority customer, he waits till the customer of lower priority who is currently undergoing service, till he completes, his service is completed. If he waits, then that system is called non-preemptive. Now, again within preemptive, then there could be preemptive resume and preemptive non-resume. So, what happens to the service that has already been done? Whether the service starts from that point onwards for the remaining service, then it is preemptive resume, or he has to be served all over again, right, preemptive non-resume. So, it means his service starts afresh. That is the situation that you will have. So, this is about the priority and preemptiveness, and there could be like many other things that you might observe, but the shortest job first. Okay. So, the requirement of the service requirement or the longest job first. Okay. So, there could be many different kind of things that you meet, but as we said, the most common one was this first come first serve. That is what would see, but there are others depending upon the application that you need. These are the fifth component. This is the fifth component that is used to describe a queuing system, and for basic systems like this might do, but there may be some other features which also need to be described to describe the queuing system completely. So, and again I caution, this is not an exhaustive list, but some of them which is also most commonly that you would see. So, for example, multiple stages of service, right. You apply for a passport, right. You would see that you will go through multiple stage. You could consider that as a stage, or right, you could think about what you call, okay, in a hospital, suppose if you want to go, you want to get this physical examination done or a full body checkup done, then what are the things that you need to go through, where you will go. So, this you could call as a multiple stages of service. Okay. Then the most important one, which is most practically it's relevant, is this particular network of queues, right. This is what you would see in most real life scenario as well as in most of the applications, because if you do not have network, then we are talking about a single system, but in most places it is not just a single system, it is network. Like after you are getting served from one place, you move to the other place, other service center, right. You get service one after the other before your complete service requirement is met. So, then you have a scenario where you have networks of queues. So, that is why the common word communication network, computer network, because these are all again network, because nothing is common, because you suppose if you are talking about a mobile network, there is a base station in this place and after some distance there is a base station there, like you are calling from this the range of this base station. So, it will capture, the signal will go to this base station and from here it is transmitted to the other one and from here and so on, or whatever is the phenomenon that you have it here, right. So, that is you have network or wherever things has to pass. So, in a production network you need to the item before it comes to a final stage, it needs to be go through different stages, right. So, networks of queues, again each one would be the network, right. Each one is a queuing system, and when they are interconnected, when the customer is moving from one to the other according to some rule, it is not that everyone will go through all, that is a different phenomenon, that is a special case, but of course in general also you could have, when we study this you will see this more. Okay. So, this network is so common to in reality to study this as a network of queues. You have to study about the single system first, then before you move to the network of queues. Okay. Then there is recycling or feedback, right. So, you are making a manufacturing some product and you do the quality check at the end of the production, and if you see there is some defect, you send it for reprocessing, right. So, you would have a recycling phenomena or a feedback phenomena that you would have. Then you will have a retrial phenomena of blocked customers. So, this is whenever the system is full to its capacity, a customer is said to be blocked. Now, what happens to these blocked customers, right. So, that is another phenomena which is again common in communication networks and systems, where this is the phenomena that we call as retrial. Retrial means that you let we are assuming in some sense the customers are in some orbit, and after a certain point of time the customer will try again to do that. Okay, he is not gone out, he is not making a new entry, already he has came to the system, but he is not in actually in the queue, but he is in some other queue in a way virtually, which is basically we call it as orbit, and from there he makes a retrial after a random amount of time. That is what you keep, right. So, this is then there could be server vacations. The server vacation is so common word, right. Server vacation is so common word, it could mean differently. Server maintenance ke liye you down it for some time, or when there is nothing that getting there is no customer, then what basically like you try to incorporate such behavior through this called vacations, right. It is a common term, but it could mean many different things depending upon the context. So, the server may take a vacation when it does not have anyone to serve, right. So, that is the meaning. Now, what happens after one vacation? So, it could be a single vacation and he comes back, wait for customers to come, or he may go on whenever he sees the symptom is free, like he can go for a vacation. So, it is called multiple vacation. So, again there could be different variations in that, okay. And there could be variations, for example, something called working vacation, meaning that in the normal rate, in working vacation situation it may serve at a lower rate, okay. For energy efficiency, like in military and other applications for energy efficient systems, like something which is operating on battery, you will not make it available the server on a full battery. So, you reduce at a lower capacity, which means you down your battery level a bit. That is what it would mean in that way, okay. Now, another phenomena could be service can only start when there is a certain number of customers in the queue, right. Maybe because the server needs some setup time, a setup cost is involved, like you are starting to start the server. So, you want some customers to accumulate, then before you start the service for the customers who are already waiting, there may be some customers waiting. This could be either based on number of customers, means until unless there are 5 customers I am not going to start serving, or there is a time, maybe after I will wait for half an hour and then until whoever comes, like, or it could be hybrid of both and so on, right. And there could be catastrophic events, there could be a link failure. So, whatever packets that have been sent up to that point of time, it has reached up to that particular link, they are all dropped. So, this is catastrophic events, right. So, again there is catastrophic, again it could be complete one, total catastrophic, or there could be mild catastrophic, meaning that it will not kill all the packet that has been waiting, but it might kill some portion. Maybe how it is decided, again there is a variations, like these are all some other features. It is not just all, there could be many different features that you need to describe. So, it is all boils down to like observing the system and describing whatever required to describe that system. The main essential features you need to describe to characterize the queuing system, and based upon that then the analysis has to begin. So, that is what it is, okay. Now, to describe this kind of queuing systems, in queuing theory we use a typical notation, because when you use this notation then the system whatever you are trying to say is easily understood. Again there is only very basic sets, More complex systems need to be described in explicit terms, but the notations would describe to some amount like the general description of the system. So, this is called as Kendall's notation because he is the one who developed this first. So, this is basically we describe through typically by these 5 elements A, B, C, D, E with the slash in between it is described. So, what are the characteristics? A denotes the inter-arrival time distribution, B denotes the service time distribution. Okay. So, if the inter-arrival time distribution is exponential, then this A and B, both are A and B, like is denoted by the symbol M. M means exponential. Ideally it could have been E, but then that would confuse with this E. So, it is M. So, M means Markovian in nature, because in Markov systems like what you would the natural distribution that arises there, the holding time is exponential. So, that is M. So, suppose if I have this A as M or B as M, that means that I have this is the one exponential in mind. D represents deterministic, EK represents Erlang type K, it is some sense related to the gamma. Of course, we have already, I mean we will describe it in the probability part, that what is the structure of this distribution that you can see. Again HK is a mixture of K exponential, and then PH is more general one, which is called phase type distributions, you will also see later in the course. G means it is general. So, it could even this G, whenever you are putting, it could mean anything, any of these also it can represent in theory, but you know when you are not able to represent by the usually accepted conventional symbols, then you use this G, and this could mean general. We will also take this to be general and independent. So, some books or some places you would find the notation GI to denote this. Typically, whenever you need to distinguish between general and independent, general and dependent, then G and GI are used. Okay. But since we generally have this only the independent sync system, so for us it is G would work to mean that it is general and independent in this case. Okay. And this the third ingredient here in this symbol is the number of servers. It could be one server, it could be two server, it could be some finite number of servers, or it could be an infinite number of servers. D represents the system capacity. Again, this could be system capacity could be 1, and if there is a single server and there is 1, that means that it is not there is no waiting space per se in that place, right. There are situations like that, which is typically called as loss systems. Okay. And there could be more capacity, and the system capacity could be infinity as well, which means any number of people can queue it. Then there is a queue discipline, which is what is E, which will be represented either by FCFS or LCFS or RS, random selection, or processor sharing, or whatever the description that might come here. Okay. Now, when we are writing these notations, the defaults that we are assuming here is that the defaults are here, or we will assume D to be infinity, which means the system capacity is infinity, and the queue discipline is FCFS. So, whenever these two are there, then these two things are typically omitted from this D and E, even without specifying. If we write something, that means this default is assumed, that the system capacity is infinity and the queue discipline is FCFS. If otherwise, it will be specified explicitly. Say for example, if I have a description of MD2, right, MD2 means that the inter-arrival times are exponential, service time is constant, and there are 2 servers, and the system capacity is infinity, and the queue discipline is FCFS. Okay. Remember here one thing that we need to look at here itself. Again, this service and the inter-arrival processes, these two are also we generally assume that they are independent, which means an arrival does not influence the service in some sense. Okay. Our arrival happening does not get influenced by this, and vice versa, right. So, these two processes are independent, there is no relationship, that is what we assume. If we assume that they are dependent, then again there will be more complexity, we will not have that at least in this course. Okay. Now, similarly, for example, MMCN. So, in this particular case, what happens that there is an exponentially distributed interarrival times and an exponentially distributed service time, and there are C servers and the system capacity is N. Okay. Similarly, GG1 in a similar way, MPH infinity, which means now the number of servers is infinity, the service time distribution is PH and M. Now, we have seen something like vacation, retrial, network and so many other phenomena. Like again, they could be represented using this as to the extent possible, but it is not that the completely they can be described using notations itself, because some might use, but that is not common or that is not standard notation for everyone to understand. So, everyone will understand with this 5 points only. Additional notation sometimes it is used if it is common within that domain of community, but it is not common, but maybe better to describe it explicitly, at least when you start, right. So, that you need to do. So, additional notations are used whenever is necessary, but they may not be uniform or commonly accepted as far as that is concerned here. Okay. So, this is all the characteristics of the queuing system which you need to describe in order to describe the system completely. Once this description has to be there in order to model a system. Now, depending upon what is the description of the system, then you try to extract a model, that the queuing model for further analysis in this case. Okay, so to pick any model, for example, as with any mathematical model, a clear understanding of the characteristic of queuing systems is essential for the successful application of any queuing model that you have here. Okay, that is typical of any mathematical model, and in the queuing model scenario also that is true. So, one needs to understand, you have to observe the system, one needs to understand the system to extract the essential features to make a model. The more and more the assumptions that you make, the model will become will go away from reality, but the essential feature should not be destroyed, but then the result that you get out of the analysis will be meaningless. So, you need to keep a balance of that in trade off it. Say for example, if you look at it, that is with respect to any mathematical model per se, but applicable here as well. Now, the observation is important because you would see that, for example, if you look at a supermarket, you have multiple counters, and which is the most common model that you can employ there. If you look at whether it is a common queue or individual queue, by the look of it, if you go and observe, like there is one queue for each of these checkout counters that you would see. So, you would see that okay, these are multiple parallel servers, and you have suppose there are 10 of them and there is 10 individual queues is the model. But if you look at if you look at the system carefully, and if you observe the system a little bit more time, you will see that suppose if against 9 counters you have queues, and the 10th one, right, which may be the 5th one for example, he served all his customers. Now, is he going to be not doing any service and he will be simply waiting for the other customers to come directly from inside the shop, not from any of these queues? What you would observe is that immediately from the other queue, someone will come to this queue and then he will start serving that particular customer. So, it is essentially, though you would mean that with jockeying, multiple queues with jockeying is what is happening, but it is not really the case. So, this could as well be analyzed as because no server is going to be free if there is at least customers waiting in the queue in the other counters, right. So, this could as well be that there are 10 parallel servers and with a single common queue, you could as well model with this phenomena. So, you have to see like which one. So, which one is more efficient. Now, you will see later that having this individual queues or a common queue with anyone can reach depending upon the availability that any of the servers it can reach. Which system is more efficient? You can intuitively also you can think, but you can also show it through analysis that which one is better. Now, the single queue, common queue is what is the better one it will turn out to be, right? Intuitively also you can feel so. Now, in this particular case, like if you analyze that they have 10 different queues, then things will be not correct, because in that scenario you have individual queue, and when there are customers waiting in the other queue, this server will be free, he will be idle, and that scenario is not going to happen in this checkout counters. So, then that model is not really an appropriate one. So, the common queue is what is the appropriate model that you would see. So, this what we mean at the first sight you would see that there are 10 different queues for against 10 different servers, but it is not really the case. The real case is that you have a common queue with 10 parallel servers. That is what you have it here. Okay. So, this kind of observation, like anything that you have to observe the system and then see like what is the best one that is happening there. Okay. That is how the model can be effectively utilized or used in the practice. Okay. So, we will stop here and then we will continue in the lecture. Thank you. Bye.